So hello everyone. I have here today a problem from the recent November 2023 Civil Engineering Board Examination. So for this problem, it's a beam system which involves a cantilever beam BD which rests on a simple span AC which are of the same material and have the following dimensions: 3 inches by 8 inches deep. And it is said in the problem that they both carry the load 1,400 pounds jointly or together. So what's being asked here is the maximum flexural stress. So in the actual exam, what is being asked is the maximum flexural stress at beam AC and also the moment reaction at point D. So how do we solve for this value? So we know that the maximum flexural stress is just the maximum moment times the distance from, or the C distance from the neutral axis to the extreme fiber of the beam, which is this, and its moment of inertia for this cross section. So C can be solved easily because we know that the height is 8, so we just have to divide that by 2 to get C, which is 4 inches. And I for rectangular sections is just BH cubed over 12. So you can easily solve for I. So that's 3 times 8 over 12. That's 128. All that's left for us to solve is for the maximum moment. And the maximum moment for a simply supported beam with a point load acting at a point not at the midspan is just this. M max is PAB over L. And let's just use formulas to um, practice our speed in solving these problems, because in the actual board exam, it's very difficult to use conventional methods in solving for moments, shear, and deflection, because um, these methods take time. So let's just use formulas instead. So, so for this maximum moment, you might think that the P is this 1,400 pound load, but it's actually not. And let's find out why. So for this system, let's try to isolate its individual components. So we can analyze the internal forces acting on the beam. So this is the cantilever portion. So we know there is a 1,400 pound load there, and there is a reaction here at D and a moment reaction at D. And since this beam BD is in contact with beam AC at point B, then there must be a contacting force here to prop this beam up, which is RB. And since there is a reaction there, that means if we draw beam AC, there must also be the same reaction at B there. And this will be the reaction at A, this will be the reaction at C. These are the same reactions since the contacting force between the two beams must be the same. So now that we know that, this reaction at B will cause the maximum moment in beam AC since there is no other external force acting on it. So M max AC is equal to RB AB over L, where A is equal to 8 feet and B is equal to 4 feet. Since A is given by this dimension here and B is given by this dimension here. Okay, so, and also L is just the total length of this entire beam, so that's 12 feet. So what's left for us to solve is actually RB. And how do we solve for RB? RB is just a reaction in this beam system, but it's not that easy to solve given that this beam system is actually indeterminate, meaning we cannot use the normal static equilibrium equations such as x, summation of forces along x, summation of forces along y, summation of moments to solve for the reactions. We need to use other equations, so equations of deflection to be um, exact. So we need to use these kinds of equations to solve for the reaction. So how do we relate the deflections in this system to the reaction at B? So we know that since this system carries this load jointly, they must deflect together. And the elastic curve, sorry, and the elastic curve should look somewhat like this. And this is just the deflection at B. So let's try to find equations which will relate our reaction at B to the deflection at B. So let's first consider this cantilever portion of the beam. So considering beam BD. So let's first draw the 2D view of this beam. So here is the 1,400 pound load. Here is the reaction at D and the moment reaction at D. And since we know that this beam is being propped on beam AC, there must be a contacting force here, which is RB. So in order to find the deflection at B for this isolated system, um, let's use the method of superposition. So for a cantilever beam with a point load at the end, the deflection at that point is just equal to EL cubed over 3 EI. But for this situation, L is the entire length of the beam, which is 8 feet. And P is either this RB here and also the 1,400 pound load. So since this load will cause the beam to deflect like this, and this reaction will cause the beam to deflect in that manner, we can assign the deflection of B to be equal to the 1,400 pound load times the length over 3 EI, and we will subtract the deflection caused by RB since it is against the assumed deflection caused by the 1,400 pound load. So that's just 8 cubed over 3 EI. Sorry, this is 1,400. So here we have our first equation. And since we do not know the deflection at B and we also do not know RB, let's find another equation which can help us isolate the reaction at B. And we can find that equation from this next beam section, which is beam AC. So considering AC. So let's draw beam AC first in 2D. Here is the reaction at A, reaction at C, and here is the reaction at B. This is 8 feet. This is 4 feet. And for a simply supported beam with a point load not located at the center, the deflection at that point is given by this formula. So that's just PA over 48 EI times 3L squared, which is the length of the beam, minus 4A squared. And A corresponds to this value, 8. So the deflection at B, where P is RB, the point load being applied in the system, should be multiplied by 8, which is A, 48 EI, times 3 times 12, which is the total length of the beam, minus 4 times 8 squared. And now we have our second equation. Equation 1 again. So we have two equations, two unknowns. We have set earlier that the deflections of beam BD and beam AC are both equal at P. So we can set deflection at B to be equal for AC, which is equal to the deflection at B for beam BD. So let's do that. It's a different color. So um, here the deflection of B at beam AC is just this. So if you can notice that I have left the value of EI as variables, since I know that they will cancel out later on. So just leave them as variables for now. So 1400 times 8 cube over 3 EI minus RB 8 cube over 3 EI. And as I've said earlier, we can factor out the EI here and just cancel it out. And all that's left will be RB. And using our calculators, we can find that RB is equal to 1,194.667 pounds. So now that we have RB, we can go back to solving for the maximum moment at beam AC. So, as I've said earlier, M max at AC is equal to, this time let's use RB, A times B over L. So let's plug in our values. 1194 times 8 times 4 for 12. So using our calculators, we can find that the maximum moment of beam AC is equal to 3,185.779 pound-foot. So before we use this value, let's convert this to pound inches first, because the final answer should be in PSI. So to convert this, let's just multiply 3185.779 by 12 inches. Since this is feet, can cancel that, and it will result with this value, 38229.344 pounds inches. So now we're ready to solve for FB max. Let's plug in our values, 38229 times our C value, which is, you have solved this earlier, 4 inches, over our moment of inertia, which is 128 inches to the power of 4. And this should be the final answer for the maximum flexural stress in beam AC. 1 point. Actually, the unit is PSI. And it's correct. So let's solve for this portion. which is the moment at D. So simply the moment at D is just, we can derive here, we can derive it from here, which is moment at D is just caused by this 1,400 pound load times the moment arm, and we need to subtract it by the moment caused by this reaction at B. So 1,400 pound load times 8 feet minus, since the rotation caused by RB is in the opposite direction of the 1,400 pound load. And with the same moment arm, we will arrive at the answer that the moment at D is just 1642,664 pound foot. And there you go. So here are the answers for this problem, and I hope you guys learned something from this video.